In this video and in the next video, we'll look at two examples from the textbook, a blending tank and a distillation column, to illustrate some concepts of process control. Expand on later throughout the semester. The first example we'll look at is this blending tank. So this blending tank combines a stream with a mass flow rate W1 and mass fraction of a solute X1 with another stream of mass flow rate W2 and composition X2 of pure A. So the mass fraction of A in this stream is 1. Now the effluent from this blending tank is an overflow line which maintains the contents of the tank at a constant volume. The control objective is to maintain the effluent composition X at some desired value that we call its set point, X sub SP. And we do that by modulating the flow rate of stream 2. Stream 2 has a control valve on it that allows us to change the flow rate. We might need to change the flow rate of stream 2, for example, if the inlet flow rate or composition might be changing with time. So the control law for this blending tank will tell us what the value of W2 should be in order to keep X at its desired set point. To determine that, we'll begin by writing material balances for the tank. Since the tank is maintained at constant volume, and if we assume constant density, then the total mass balance for the tank says that there's no accumulation. So the flow rate in has to equal the flow rate out. And here we use the bar over each of these variables to indicate that these are at their steady state design values. So W1 bar is the steady state value of W1. We'll also write a component A mass balance. The component A mass balance at steady state says that there's no accumulation and that the amount of A coming in is equal to the amount of A leaving. Now we can ask the question, what should W2 bar be to keep X bar at its set point, X sub SP? To answer this question, we'll substitute for W bar, X bar, and X2 bar in the component balance equation. So W bar can be obtained by solving the mass balance for W bar and thereby eliminate W bar using the sum of W1 bar and W2 bar. Since we want to keep X bar at its set point, X sub SP, we'll substitute X sub SP in for X bar. And X2 bar, that is the mass fraction of the solute in stream 2, is equal to 1 according to the diagram. So we can eliminate X2 bar and just replace it with the value 1. The resulting component balance here can now be solved for W2 bar. And we find that W2 bar should be W1 bar multiplied by this ratio of the difference between the set point and X1 bar and 1 and the set point. Now suppose X1 varies with time. So it is no longer going to be a steady state value X1 bar, it's going to be a function of time. How can we ensure that the outlet composition X is maintained at X sub SP? That is, that the effluent composition is maintained at its set point. We can think of several ways that we might control X at its set point. One would be to directly measure X, and then based on that measurement of X, we could adjust W2. If X is increasing, we might need to decrease the flow rate W2, and if X is decreasing from its set point, then we might need to increase the flow rate W2. Another scheme might be to measure X1. Since X1 is going to vary with time, if we know how X1 varies with time, we could measure it and then adjust W2 accordingly. Of course, that suggests that we could also measure both X and X1 and make the necessary adjustments to W2. If we know something about how X1 changes with time, for example, maybe we know that X1 oscillates, deviating a little bit positive and a little bit negative from some nominal average value, then we might simply control X by just making the tank larger. A large mixing tank will average out the fluctuations in the incoming composition, and maybe we don't need any measurements or adjustments in W2 at all. So if we were to use option 1, the instrument diagram shown here adds a composition analyzer transmitter to the effluent stream which sends an electronic signal, which we will always indicate with a broken line, to an instrument that's called a composition controller. That composition controller then sends a signal to the control valve. If x is less than the set point, then we would want W2 to increase, and if x is greater than the set point, then we would want W2 to decrease, because W2 is the flow rate of a stream that contains pure solute. We can write a control law that accomplishes this by setting W2 equal to its design condition plus some weighted difference between the set point and the measured value. That is, the deviation of W2 from its steady state design condition is proportional to the difference between the set point and the measured value. This is an example of what we call feedback control. If we were to instead use option 2, how would we decide what W2 should be? In this case, we can use the component A balance to determine exactly what W2 should be. We solved this earlier when we were finding what W2 should be for the steady state condition. Now we just make x1 a function of time and W2 a function of time. In this instrument diagram, the composition analyzer transmitter now has been moved to stream 1 and sends its signal to the controller, which then sends its signal to the control valve. We'll use instrument diagrams that contain symbols like this throughout the semester, where electronic symbols will be indicated by broken lines. Occasionally we'll also use pneumatic signals, and pneumatic signals are indicated by thin solid lines with double hash marks on them. We said earlier that method 1 is an example of what we call feedback control. Method 2 is an example of what we call feed-forward control. The distinction between feedback control and feed-forward control has absolutely nothing to do with the directions in which the arrows are pointing in the diagram. Rather, in feedback control, we measure a controlled variable, and we use the measurement of the controlled variable to decide how to change the manipulated variable. In this case, and in most cases, the manipulated variable is a flow rate, and it can easily be identified by a control valve. So the manipulated variable for both of these control schemes is the flow rate W2. Notice in the feedback control, the disturbance variable is not measured. In fact, we don't even need to know what the disturbance variable is. The disturbance variable could be x1, it could be the flow rate W1, it could be a leak in the tank that's not even identified in the diagram, it could be a thunderstorm dumping rain into the tank. The composition could be disturbed by anything, and that disturbance in the effluent composition would be measured and accounted for by the feedback control loop. One disadvantage of feedback control is that it cannot take action, that is, it cannot change the manipulated variable until after the controlled variable x deviates from the set point. Notice that if x does not deviate from the set point, the controller won't do anything, and W2 will remain at its steady state design condition. On the other hand, in feed-forward control, the controlled variable, in this case x, is not measured. Instead, a disturbance variable is measured. Feed-forward control has a distinct advantage over feedback control. The controller can take action to reduce or prevent a disturbance on the controlled variable even before that controlled variable is affected by the disturbance, especially if the disturbance variable can be measured far upstream of the controlled variable. However, feed-forward control has some serious disadvantages. For one, it requires a model of the process that can be solved to determine what the manipulated variable should be. And that model may contain approximations or errors, meaning that our manipulated variable will not track exactly what it needs to do in order to eliminate disturbances. Furthermore, feed-forward control can only account for modeled and measured disturbances. This feed-forward control scheme may do an excellent job of rejecting disturbances if those disturbances are fluctuations in the composition x1, but it will do nothing to reject disturbances if the disturbance is the flow rate W1 or one of the other things we mentioned, like a leak in the tank or a thunderstorm, because those are not measured. The feed-forward controller can take no action against disturbances that are not part of the model. Throughout this course, we'll represent control loops using instrument diagrams like the one shown here for the feedback controller, and we'll also use block diagrams like the one shown here. Components of the process and instruments in the control loop are represented by blocks, such as the control valve and the sensor transmitter shown here, or by groups of blocks, such as this group of blocks that represents the controller. The arrows represent important signals or process variables, and the block diagram shows us how information is transmitted and used within the control system. This block diagram shows both physical process variables, such as the flow rate W2, and it also shows instrument signals, like this signal P, which represents the signal coming out of the controller and going into the control valve. In the block diagram, each block represents a mathematical operation. We'll learn a lot more about block diagrams, and we'll actually use block diagrams to build mathematical models of control loops later on in the semester. In the next video, we'll take a look at this example of a distillation column.